describing wave motion, you're going to want to cut off the border, cut out all boxes except for that last row. You're going to need 5 colors for this. Okay, let's take the first one, and we're going to glue that in the graph. Don't put too much glue on it because we're going to be writing on it. Glue it in about a line down, maybe a little bit more from the top. Okay, so remember when we're talking about waves, all right, wave motion, this is a combination of harmonic and linear motion. Okay, so some things we've learned from harmonic we're going to apply, and some things we learned from linear we're going to apply to describe the motion of a wave. Now, if you look at the graph, you're probably thinking that looks a lot like a harmonic motion graph, right? The key difference there is that is distance on the x-axis. All right, so my x-axis value is distance. In a harmonic motion graph, that x-axis is time. Okay, but other than that, they look pretty much the same. So we are going to start off, I'm going to use purple. We are going to highlight one wave. And one wave looks exactly like one cycle. So I'm going to start here on the 1 meter in the x-axis there. Go all the way up, all the way down, back to the middle. All right, that is one wave. Now, there's this nice thing about waves that they actually have, there's actually a name for the very, very top of that wave. It's called the crest. All right, just like the toothpaste. And there's a name for the bottom of the wave. That very, 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 very bottom there, that's called the trough, T-R-O-U-G-H. That G-H has an F sound to it, trough. All right, something that comes directly from harmonic motion is amplitude. Amplitude is exactly the same. All right, amplitude is exactly the same. Now, in order to be able to figure out the amplitude, you need to identify the equilibrium position. Now, I think you guys understand equilibrium position enough that we don't have to actually highlight it, but let's go ahead and label it. Okay? So equilibrium position, okay, that is that right there. That's your equilibrium position. Now, something that is unique and new to waves is the idea of wavelength. Okay? Let's take that little piece of paper. I'm going to glue it in below to the left. Okay? Wavelength is the length of one wave. Okay? The length of one wave. So I'm going to make that green. Now, if you look carefully, there's a funky symbol here. That is not from our alphabet. That's from the Greek alphabet. Okay? It's called lambda. Okay? That little symbol represents wavelength. Now, the length of one wave. So, looking at our purple wave here that we've highlighted, if you start from where you start to where you end, and you measure that, that is the wavelength. Okay? So, go ahead and put a little lambda right there. Wavelength. We can measure the wavelength there along the equilibrium position, or we can measure the wavelength from crest to crest, right there. There's another wavelength, lambda. Or we can measure it from trough to trough, from right there to right there. Any way you measure it, that wavelength is always going to be the same for that wave. So my question is this: what do you anticipate the units of measure to be for wavelength? Very good. Your little hint there, length, it's meters. Now, a concept that we pull from harmonic motion is frequency. We can measure the frequency of the vibration of the particles. And in this case, instead of being the number of cycles per second, it's now the number of waves per second. Okay, what are my units of measure for frequency, class? Hertz. Spell it out first. H-E-R-T-Z, abbreviation H-Z. Now, remembering that waves are both harmonic and linear motion, now we're going to talk about the linear aspect, the velocity of the wave. Okay, so velocity we discussed when we were talking about linear motion. Okay, velocity of a wave can apply because we see how fast the wave moves from one place to the next. So this is the linear speed of a wave. Now notice they put the little W on there, so you know that we're talking about the velocity of a wave, not just the velocity of anything. Okay? Because it has its own formula. So we have to give it a slightly different variable because it's not the exact same formula. And here is the formula for the velocity of a wave. Give yourself space above and below it. Now, before I get any further, what do you anticipate the units to be for the velocity of a wave?
Meters per second.
Very good. Meters per second. Just meters per second. All right, so let's take a good look at our formula here. VW, velocity of a wave. What does the lowercase curly f look like? What does it stand for? Frequency. What does that funky symbol that's from the Greek alphabet called lambda stand for? Wavelength. The length of one wave, and the units of measure for wavelength are meters. And what are the units of measure for frequency? Hertz. Now, if you think about it, hertz is how many, in this case, waves happen per second. And this is how long one wave is. So basically, we're multiplying how many waves happen per second, multiplied by the length of the wave, to figure out how quickly that wave is moving. So our units for velocity of a wave, meters per second. Here I've provided the formula rearranged. All right, I use the triangle to do that. All right, frequency and wavelength, they're side by side. That puts the velocity of the wave on top. If I want to know the frequency, I cover it with my finger. I get the velocity of the wave over wavelength. If I want to know the wavelength, I cover it with my finger. I get the velocity of the wave over the frequency. Okay, so there's the formula with its rearrangements. So basically, that's all the information you need, not only to be able to analyze a wave, but to be able to describe it, use words and formulas as needed to calculate it.